as always, I'm going to start with a review. So we're doing, remember, Fourier series representation of continuous time periodic signal. We know what the synthesis expression is, right? So a periodic signal can be represented as a superposition of complex exponentials, and the Fourier series coefficients, which are a sub k's, can be found through the analysis equation, which is this form. And then we started talking about what are the properties of Fourier series, and using some of those properties, we actually found out KD determining the Fourier series coefficients of some signals becomes easier. So we talked about linearity, which is straightforward, and then time shifting. So if you have x of t minus t naught, and you compute the Fourier series coefficients for that, remember x of t is a periodic signal. That turns out the only change that's there in the Fourier series coefficients is a change in the phase, right? So the new Fourier series coefficients are AKs, the old Fourier series coefficients, times this exponential term e raised to power minus jk omega naught t naught. So this is a complex number of magnitude 1 and some phase being multiplied with the previous coefficients, right? If time reversal just says, if you flip the periodic signal in time, then the Fourier series coefficients are also flipped, right? Then we talked about time scaling. Let me just skip over that. And we then spent quite some time on conjugation, right? So if there's a signal x of t, and if I take the conjugate, right, we said kg, of course, the Fourier series coefficients or the periodicity properties do not change. The period remains the same, and the signal is still periodic with the same period, right? And the Fourier series coefficients of the conjugate of the signal is a of minus k conjugate, right? So there's a conjugate missing here, right? So if the original Fourier series coefficients were ak, the new Fourier series coefficients after the time domain conjugation are given by a conjugate of minus k, right? Now, because of these properties, in particular the conjugation property and the time reversal property, we were able to derive conditions. Okay, what happens, for example, which is condition number A, and this I'm going to ask you, okay, what happens if x of t is real? What property does the Fourier series coefficient satisfy? What do you think? So if the signal is real, right, what properties do the Fourier series coefficient satisfy? Not necessarily, Daniel. So when x of t is real, so you can browse through your notes. Not necessarily, once again, they're not real. Coefficients are not real. It said something else. Who's going to unmute themselves and let me know? Like something we did in the last class. Right? If x of t is real, right? Hassan, that's not exactly true. Right? So it turns out if x of t is real, the Fourier series coefficients are conjugate symmetric. They're conjugate symmetric, right? What that means is that a k is equal to a minus k conjugate. So that's something we derived. So they're conjugate symmetric, right? They're not necessarily real, but they are conjugate symmetric, right? And it's because of this condition that a naught is real, right? Because if I plug in k equals 0, that means a0 is equal to the conjugate of a0, and that must mean the a naught must be a real number, right? So this is the conclusion that we made. What about x of t is real? I would very much like if you could unmute yourself and answer. What if x of t is even? What can you say about the Fourier series coefficients? Ji Ibrahim.
सर फिर सिमेट्रिक होते हैं कोएफिशिएंट्स.
Coefficient symmetric होते हैं, right? So इसे कि जी ak is equal to a of minus k, right? And if x of t is odd, they are anti-symmetric. Ak must be equal to minus a of minus k, and this must mean that a naught is, what is a naught?
सर 0.
Is 0. Good. Who was this? Ibrahim. All right. If x of t is real and even, if x of t is real and even, what can you say then?
The coefficients must be real.
Right. So Daniel, yes, that's correct. AK is real. Right. So if x of t is real and even, then we say that AK is actually equal to A minus K conjugate. So that's the first condition. And AK equals A of minus K. That's because of the evenness. And this implies that AK equals AK conjugate. Right. So that means they're real coefficients. Right. And if x of t is real and odd, um, because of the fact that they're real, AK equals A of minus K conjugate. And because the fact that they're odd, AK equals A of minus A of minus K. And this implies that AK equals minus AK conjugate. And this means that they're imaginary, purely imaginary. Right. So this is something we good. This is something we concluded as at the end of our last class, I think. Right. So before we talked about that example in the last class. Okay. Now, the reason why I went through these again is because this is something that we're going to end up using in one of the examples that we're going to do in just a bit. Right. Any questions about this before I move on? No questions. Okay. Right. So I want to wrap up this discussion on the properties of Fourier series, and the last property that we're going to do is Parseval's relationship, right? So Parseval's relationship. Now so we're going to try to derive the Parseval's relationship instead of me just giving you the answer, right? The question we want to ask is, KR, if I compute the power in the periodic signal within one time period, right? So that's power in one time period. That is equal to 1 upon t. And this is integral over any period capital T, right? And this is x of t absolute squared dt, right? So remember, this is the, like we did in chapter 1, this is the power in a continuous time signal. And it's actually defined as over one period, but this is actually the average power. Even if I take the limit capital T going to infinity, this is still going to be satisfied. Take it from minus t to plus 2t. Remember that application. Remember that. I mean, there was, I think, a homework problem on this as well. All right. Now the question is, can we relate this power to the Fourier series coefficient somehow? And that's what Parseval actually was, which is the name of a person. I mean, name of a scientist, a mathematician who derived this relationship. Okay, this power is actually related somehow to the coefficients themselves. Okay, so in order to go that route, I mean, what do you suggest? I mean, if I were to ask you, yeah, इसको थोड़ा सा manipulate करें so that you get a relationship as a function of the Fourier series coefficient. So what do you think would be the first step? क्या करें, right? So x of t I know is, I'm assuming it has a, so Umar is right, so we just apply the definition. So x of t is a summation a k e raised to power j k omega naught t. Okay, and if the Fourier, I'm assuming that the Fourier series representation exists for this periodic signal. Okay, now if this is the case, and if I plug in this into the power, which is 1 upon t to capital T x of t absolute squared dt, which I know is actually equal to 1 upon t integral over t, and this is x of t times x conjugate of t, because x times x conjugate is the absolute squared times dt. And then I plug in this x of t here and here as well in the conjugate. Okay, so what do I get? So I get 1 upon t, and I have an integral, and x of t is summation k going from minus infinity to plus infinity, a k e raised to power j k omega naught t. So this is x of t, right? So this is x of t. All I've done is I've just plugged in what x of t is, in terms of its Fourier series decomposition, right? What about x conjugate of t? Then I have another term here, which is x conjugate of t. And in this x conjugate of t, let me use another variable for the summation and not k, right? And the reason for that is going to come clear in a little bit. So this is am e raised to power j m omega naught t. Sorry, so this is conjugate, and this is minus dt, right? So this thing here, this whole thing inside the brackets here is actually x conjugate of t. So all I've done is just plug in x of t here, plug in x conjugate of t here. Okay? Any questions here before I move ahead? Yes, sir.
So you're multiplying by the conjugate because this is a complex number?
Exactly, because it's a complex signal. And if I were to compute the absolute value of a complex signal, how do I do that? I multiply the number, the signal by its conjugate. That's going to give me the absolute squared. That's the definition of absolute squared, right?
Please.
Okay.
Thank you.
All right. Any other questions? All right. So Asad, if you can lower your hand. All right. So this is, what do I do next? Can I simplify this? Can I simplify this further? What do you think? Hassan, any ideas? Hassan Ahmed?
Sir, you can take the summation of m to the other side, and then you can combine these like the exponentials and the
Okay.
k's and am's.
All right. So what I will do is I will take the summations outside of the integral, right? So this is because everything is linear. So the summations can come out of the integrals. So this is minus infinity to plus infinity. This is m going from minus infinity to plus infinity. And this is integral. And I combined everything up, right? So this is ak times a m conjugate. This is e raised to power j k omega naught t. And this is e raised to power minus j m omega naught t, and this is dt. Okay. So actually what I'm doing for you is one of the end of chapter problems, right? So this is part of one of the end of chapter problems in your textbook. So we're just doing this in class. Okay. So this is 1 upon t. This summation is going from k equals minus infinity to plus infinity. This is m going from minus infinity to plus infinity. I can take out AKs and AMs outside of the integral as well, because they are not a function of time, right? So this is t, and this is e raised to power j, and this is k minus m omega naught t, right? So it just, any questions here, right? So if I multiply e raised to power j k omega naught t times e raised to power minus j m omega naught t, I mean, the powers just add up, right? So, so this is what I get, right? So integral over one period of what e raised to power j times k minus m omega naught t, right? Any ideas of what this is equal to? This is something we've done actually earlier when we were deriving the analysis equation. So what do you think this is?
This should be the delta function, right? Delta km.
Excellent. Excellent, Hassan. So this is what we use in the definition, in the analysis, in the derivation of the analysis equation, right? So we found out from over there, and what are the reasons behind that? I would urge you to go back and review that. You still have lingering questions, just stay back after the class and I'll explain. This is equal to 1. Actually, this is equal to t. This turns out to be equal to t when k is equal to m, and this is equal to 0 when k is not equal to m. Okay, so what happens therefore, right? So what I'm saying is, okay, this is 1 upon t. This is summation k going from minus infinity to plus infinity, or rather, let me use the following here. So this is when m is equal to k and m is not equal to k, right? And here I have a summation. So, and this is AK. This is m going from minus infinity to plus infinity. This is am conjugate times t e raised to power j k minus m omega naught t dt. What can I say about this entire sum now? Like, what is this entire sum equal to? If I can have somebody other than Hassan try to answer this. What is this entire sum equal to? When I know, okay, this thing here is equal to a non-zero value only for one value of m, and that value of m is equal to k. For all other values of m, this integral is equal to 0. So within the summation, कौन सी चीज बच जाएगी? जी इब्राहिम.
Sir, it will be
Okay,
a की
Asad,
power.
Asad, आप
सर वो अंदर सर टी आ जाएगा और वो a का जो सबस्क्रिप्ट है वो k बन जाएगा.
Excellent. Ibrahim, do you have the same answer?
जी सर.
ठीक है, right? So once again, the reason for that is okay. So let me summarize what they said. They said, in this summation, only one of the term is going to be singled out, and that term will correspond to m equals k, right? And I am really, really happy with Asad, Khalid, and Ibrahim, and I'm sure the others had the same answer as well. Didn't get a chance to raise their hands, right? So only one of these terms is going to be left out, and that term is going to correspond to that value of m, which is equal to k, right? So this entire term here turns out to be equal to a k conjugate, right? Times t, by the way. So this is something you missed out, right? Because when m equals k, this integral is equal to capital T. So the capital T multiplies with it, right? So what do I get here? So then I get 1 upon t, and this is summation k going from minus infinity to plus infinity, a k times a k conjugate times capital T. This capital T cancels with this, and this is k going from minus infinity to plus infinity. This is absolute value of k squared, ak squared, right? So what we've essentially done is proved what Parseval proved so many years ago, right? I don't exactly remember or off the top of my head kab tha ye, but many, many years ago, right? So the conclusion is that this power, so let me write down the conclusion here, that this power in the periodic signal, one of the other ways to find that power, if you knew the Fourier series coefficient, is just to take the Fourier series coefficients, take their absolute values, and just sum them all up. Okay? So if you have the Fourier analysis, you don't need to go about computing those tedious integrals. You just find out what the Fourier series coefficients are, take the absolute squared, and sum them up. Okay? So this is what Parseval's relationship is, right? I just want to briefly just highlight what AKs are here as well. So 1 upon t ak e raised to power j k omega naught t absolute squared dt and over t, right? So what I'm doing is I'm just trying to find the power in the contribution that there is because of the kth harmonic in the periodic signal, right? So remember, the periodic signal is a sum of all of these harmonics, right? And each one of the harmonic is multiplied by a coefficient a, right? And all I do is I just pick up one of the kth harmonic and see कि उसके अंदर कितनी power है, right? And if I compute this integral, this is 1 upon t, and this is integral. This is ak absolute squared, because e raised by jk omega naught t ka absolute value is 1, and this is dt, and this turns out to be equal to ak squared, right? So in that sense, what I'm saying is that ak squared is actually equal to the power in the kth harmonic. Right? Average power in the kth harmonic component, right? In that sense, the power in the overall signal is equal to the sum of the powers of each and every one of the harmonics. Okay? take a moment to think about this when you go back, right, after the class as well, and see this in general is not true. If I add two signals up, x1 and x2, and I ask you to find out the power in the sum, that power in the sum of the signal is not necessarily the sum of the powers, right? But in this case, it is. It is. So that's because of some special properties of these e raised by j omega naught t. And I can try to make connections with vectors as well, orthogonality vectors, 90 degrees, and so on and so forth. But I think that would take the discussion further away. If you are interested, I can maybe discuss this offline with some of you, right? Whoever is interested. G. Hassan Shabir.
Sir, if we take the coefficients of both of those signals, which you just said, that if we add them up and then individually apply this power property on them, then their summation will be equal.
And so, Hassan, that depends कि वो दो जो signal आप add कर रहे हैं वो आपस में कोई property satisfy करते हैं या नहीं करते हैं, right? So here's the point: if I give you signal x1 of t, and I add another signal x2 of t, right, and this is x of t, right, and I ask you to find the power in x of t, right? So that means that this is 1 upon t, absolute of x of t squared dt, right? This may not necessarily be equal to 1 upon t x1 absolute squared of dt plus 1 upon t x2 absolute of t squared, right? So this equality is not true in general.
Okay.
Right? This is only true when the cross terms, you see there's going to be a cross term here, right? So 2 times x1 times x2 and the real part of the conjugate of x2 and the real part of that. You go about and do that. जब तक वो integral 0 नहीं होगा तब तक this condition will not be satisfied. And when that integral is 0, we say that the signals are orthogonal. That's a dot product अगर आप vectors के साथ relate करें. So once again, as I said, for those of you who are interested in some advanced concept, you want to learn more, we can have those discussions offline after the class. Okay, but as far as this discussion is concerned, what we're going to stick with is this result, which is this result here, which I'm going to box. Right, this is the Parseval's relationship. Okay, right. Any questions before I do an example? All right. Okay. So this example is, I believe, from your textbook. And the purpose of doing this example is, once again, to try and link up all of the properties and see how we can use them for some problem solving. Okay. Now here's the example. Here's the exercise. The statement that you're given is, okay, you are given the following statements about a periodic signal x of t, right? And those are the following. So there's condition number 1, and that says, okay, the signal that you're given, x of t, is a real signal, right? This is something we know. We also know that x of t is periodic with period t equals 4. All right. There's a third condition we know, and that third condition is that the Fourier series coefficients a sub k's are 0 for any value of k which satisfies the absolute value of k being greater than 1, right? Not equal to 1, but rather greater than 1. Right. And the fourth condition is that the signal which has Fourier series coefficients given by bk equals a minus k times e raised to power what was it, j k pi by 2 is an odd signal, right? So this is perhaps the most complicated of these or sophisticated of these. All right, here's the last condition that's given to you, which is the average power in the signal, which is the following. The absolute square. This turns out to be equal to half, right? This is half. Okay. Now the statement is, okay, given all of these statements or given all of these conditions, determine x of t. Right. So you're given all of these conditions about the signals, in particular some properties of the Fourier series coefficients of this periodic signal. You don't know what the time domain signal is. And from these conditions 1 through 5, we are required, if we can, to determine what the signal, the time domain signal, the periodic signal, time domain signal x of t is, right? That's our exercise problem, right? So how do I go about this? Kya karna chahiye solution? Any ideas? Any ideas what? So how many Fourier series coefficients? Ji Hassan, go ahead.
So I think Fourier coefficients हमारे 3 होंगे.
Yeah.
Right, because we'll have 1, -1 and 0.
Okay.
और हमें B case दिए हुए हैं.
Right. So we know that since AK is equal to 0 for absolute value of K is greater than 1, we know that the only possibly non-zero Fourier series coefficients are which one?
1, -1 and 0.
Right. So they are A minus 1, A naught, A0, and A plus 1. So these are the 3 Fourier series coefficients that contribute to the periodic signal. All other Fourier series coefficients are 0, right? And moreover, I also know that since t equals 4, then omega naught is 2 pi by 4, which is equal to pi by 2, right? So this is something I know. Now, if I were to apply the synthesis expression, so what kind of a signal would x of t look like? So x of t, so using the synthesis expression, I know that x of t, the Fourier series decomposition can be written as summation k equals minus infinity to infinity, a sub k is e raised to power j k omega naught t. And this implies that x of t is equal to a minus 1 e raised to power minus j omega naught t. Omega naught is pi by 2 plus a naught, and omega naught times e raised to power omega naught times 0, that's just equal to 1, and plus a plus 1 e raised to power j pi by 2t, right? So this time domain signal looks of this form. This is equation number, let's say A, right? So what do I need to determine? Therefore, in order to determine the time domain signal, so if I can somehow determine these 3 coefficients, A1, A plus 1, A minus 1, A naught, that would be enough for me to determine x of t itself, right? So we only need to determine, A minus 1, A naught, and A plus. And if we can do that, so that means we know the entire time domain signal, right? Now the question is, how do we determine what A minus 1 is, what A plus 1 is, and A naught is? Now here are some, using some of the properties that we've derived, right? Since the signal is real, what can I say about the coefficients? So if the signal is real, what can I say about the coefficients, these A minus 1, A plus 1, and A naught? Ji Ibrahim.
Sir, conjugate symmetric होते हैं.
Conjugate symmetric होंगे.
A1 और A-1 conjugate symmetric.
Right. So that means कि जी A1 जो है would be equal to the conjugate of A minus 1, right? And what about A naught? A naught would be? What about A naught? What can I say about A naught? Umar, why do you say it's 0?
तो A not real होगा.
A naught is real. Right? So who was this? Ibrahim, right? Okay. Now, let's use property number 4 and see what it says, right? So let me zoom out a little bit so that. Okay. This is the property number 4, which is the signal with Fourier series coefficients given by BKs equals A minus K times e to the power JK pi by 2. That's odd, right? So the signal which corresponds to corresponding to BKs is just a, what kind of, is a shifted and flipped version of x of t, and therefore must be real. Right? So if bk equals e raised by minus j, e raised by j k pi by 2 times a of minus k, so that means the new signal which has Fourier series coefficients bk's relate to x of t through a time reversal operation and through a time shifting operation. I know that if the original signal x of t is real, right, flipping it and time shifting it still maintains its real nature. So because of that flipping and shifting, the new signal will also be real, and therefore that must also satisfy, BKs must also satisfy conjugate symmetry properties, right? But we also know that this signal is odd. Since this signal is odd, what can I say about B0?
इवन पे सर 0 हो जाएगा ना तो.
Right? अच्छा, दोबारा बोलिएगा please.
सर वो इवन पे फिर 0 हो जाएगा ना.
Since the signal is odd, what can I say about B0? 0 हो जाएगा. Is that what you're saying?
जी सर.
All right. So B0 is indeed equal to 0. Since the signal is odd, we just found out in the review that the Fourier series coefficients corresponding to an odd signal is 0. The B0, the DC signal, DC coefficient corresponding to an odd periodic signal is 0, right? So therefore B0 is 0. And this implies, I can say something about, since BK is equal to e raised to power j k pi by 2 times a minus k, we have what? What can I say about A naught? Ibrahim says, excellent. Excellent, right? So we have A naught must be equal to 0. Right? Because B naught is 0, therefore A naught must be 0, because anything multiplied by 0 is a 0. Right? So now we're left with just two unknowns, and those are A plus 1 and A minus 1. Right? Achha. Now, since the signal is odd, since this signal is real and odd, what can I say about B plus 1 and B minus 1? What can I say about B plus and B minus 1 if the signal is real and odd? Hassan says conjugate symmetric. It's more than that, Hassan. अगर unmute कर लें अपने आप को, please. Right? So the signals, those coefficients are conjugate symmetric, right? Because, right, so I already have the answer here. Because they're conjugate symmetric because they're real. But odd होने की वजह से क्या additional चीज आ रही है? So Hassan, I'll let you speak. What do you think?
Sir, I'm not sure.
You're not sure. Okay, that's fine. That's fine. Ibrahim?
सर वो imaginary होते हैं purely, real part
Purely
0 होता है.
imaginary, as Daniel says in the chat box as well. Okay, they must be purely imaginary. So BKs are imaginary. I mean, there's no real component to those BKs because the signal is real and it's odd, right? Now, so let's try to use this to determine what A's are therefore, right? So B, since BK equals e raised to power j k pi by 2 A minus k, this implies that B1 equals e raised to power j pi by 2 times A minus 1, right? And which is equal to what? What is e raised to power j pi by 2? So let me, I mean, other people here as well. Let's see. Mustafa Siddiqui. So what do you think e raised to power j pi by 2 is? Mustafa, are you there? Okay. Abdullah Ali. You have the answer.
-1.
Right. So e raised to power j pi by 2 is not
-1.
-1. No. Right. So their answer is in the chat box already. Right. So the people say this is e raised by j pi by 2 is actually j, which is correct. Right. So this is equal to j times A minus 1. Okay. And similarly, B minus 1 is e raised to power minus j pi by 2 times A minus 1. What is e raised to power minus j pi by 2? अगर इब्राहिम, मुस्तफ़ा and Hassan, अगर आप मुस्तफ़ा ने जवाब दे दिया. Okay. Mustafa, if you can unmute yourself and tell me what is e raised to power minus j pi by 2 is. And if you have a problem with your mic, no worries, just type it up. What do you think e raised to power minus j pi by 2 is? Okay, Asad right?
सर माइनस ही होगा.
Minus j होगा. Excellent. Right? पहले क्यों नहीं बोला यार?
सर वो मुस्तफा से पूछ रहे थे आप.
मुस्तफा बोल रहा था. All right. Right. So this is minus j times A plus 1. Okay. So if B1 is purely imaginary, and I know that B1 equals j times A of minus 1, what can I say about A minus 1? Once again, the question is the following. If I know, right, so if I know that B1 is purely imaginary, right, and B1 equals j times A minus 1, what can I say about A minus 1? Somebody other than Daniel? Usman? Usman Nadeem?
Yes, sir.
So if A minus 1 is, are you sitting with everybody else? Usman?
Yes, sir.
बाकी लोग
I'm
क्या
in a
करें?
lobby, double lobby.
Right, double
Sir, वो मेरे साथ ही attend कर रहे हैं lecture.
Right. Okay, so what do you think? If there's anybody else with you who can jump in and tell me, yeah, what is A minus 1?
अस्सलाम वालेकुम सर.
वालेकुम
जी सर.
कौन है जी? मसना है?
मसला है.
यस सर मैं सर असल में वो ये उस्मान का मोबाइल पहले ख़राब हुआ तो इसने ना मेरे मोबाइल से पावर शेयरिंग चार्ज किया हुआ है.
Okay.
तो मेरा मोबाइल डेड है and I didn't bring my laptop.
Okay.
तो बेचारे का
Can you
problem
see
चल
the
रहा है.
screen?
Yes, sir. Yes.
Okay. What do you think if B1 is purely imaginary? What
Yes, sir.
should A minus 1 be? What can I say about A minus?
Sir, if it's purely imaginary, then
Conjugate.
I think because